Hello. Let's get started. Last class, I had given you an idea about a very important problem in optimization, traveling salesman problem, and presented to you an overview of 3 different approaches to solve such a problem. Hopefully, that served as an example of motivation for the course, and we will revisit 2 other approaches. The brute force, there's nothing much to say, but 2 of the other approaches, the dynamic programming and linear programming, linear integer programming, in due time towards the second half of the course. The first of the half of the course, we do have to build up some foundational concepts that will be important for solving another kind of optimization problem. If you remember in the very first class, I had mentioned this to you, that you can think of an optimization problem as a problem where you have a function and you may want to find where that function f of x, where that function f of x takes the value 0. An application being extrema of functions, where the critical point is given by the derivative of the function set equal to 0. So it is important, and it's not only for one-dimensional problem. This applies equally to higher dimensional problems, multivariate functions, as you will encounter when you learn about, when I present to you about the gradient descent method and its different avatars. Something that finds applications in AI, neural networks, to be specific. So which is why we care about these kind of problems. And these problems are known as root finding problems, because x star happens to be the root of the function f of x. There are many numerical strategies to find the root of a function. In this class, not in this particular lecture, but in this class, in this course, we will learn 2 or 3 of them. Today we will learn one of them, which is known as the bisection method. All these numerical techniques will be iterative approaches, which means that the algorithm that you will write, or what I will write, will hopefully converge to the root starting from an initial guess over multiple iterations. So these are iterative approaches. Of course, there will be questions that will come up. Questions like, will a given iteration always converge to the root? That would be useful to know, right? And secondly, if it does, how fast will it converge to the root. And fastness or speed in this case is implied by the number of iterations it takes, starting from the initial guess to converge to the desired root x star, or very close to it. So these are two matters of concern for us that we will talk about: convergence, whether it does or not, and speed or order or rate of convergence. Of course, if an iterative method is very slow, then perhaps it's not a great thing to try for that particular problem, and you might have to resort to some other approach. So what is the bisection method? Well, let us say we have a function, f of x, whose root we want to find, and I will present the one-dimensional case now. So this function f of x is a continuous function. C stands for continuity, so continuous function in the interval a comma b. A and b are two real numbers. Then can you suggest a check that guarantees that there is a root of f in this interval? Correct. So one value, which values? Or vice versa, right? So there exists a root x star such that f of x star is equal to 0 if and only if f of a times f of b is what? Negative. You see, if I have a function like that, if this is my a, this is my b, then it has to flip sign at the root. So this is my first check, only if the function is continuous. Okay? All right, so how can I make use of this fact and come up with an algorithm? That's the question. So it's iterative, so what would I do? I'll start a while loop or do while loop while my iteration is less than some max iteration criteria that I might choose, the max iteration steps. While this happens to be true, I will check if f of a times f of b is less than 0. If it is less than 0, and because this is bisection, so as the name suggests, I will keep halving the intervals, because if this is true, then there is surely a root within a and b, so I can reset a new candidate for my boundaries, which is the midpoint between a and b. Set another c, which is a plus b by 2. Okay? Now, after I set c equals a plus b by 2, I'm going to check again. If f of a times f of c is less than 0, then where will I set my new boundary? So this is my function b. This is a plus b by 2 is somewhere here. And this is my f of c. F of a times f of c is negative, so I can ignore about what is going on here between c and b and set my c as my new b. Correct? So then I will set my c as my new b. Else if f of a times f of c is greater than 0, then I will do the reverse. And there is also a possibility, else if f of c equal to 0, then my x star is c, and I break out of the function. Yeah, b is assigned to c. B is my boundary. I set my b as c. A is my boundary. I set my a. Thank you. Search. I'm not sure what are we searching here. The root. So what do they do in the binary search? Sort is what I would think. Binary sort, right? Search. Well, here, I mean, this is a type of search problem, but generally, if you're thinking about any random number, you're searching a number, you have to arrange it in some order first and then do the search. Okay, yeah, similar kind of idea. Okay. Yeah, please mark this correction. It's the boundary which is set to C and not the other way around. Thank you. And I continue the loop. Of course, I increment my I and I continue the loop. Yeah. So that two root business we haven't talked about now. Maybe I will talk about in one of the lectures. Perhaps for all the methods, I'll combine and discuss that. So for now, hold on to the thought that there is one root. Yeah. Else if I equal to I plus 1, continue the loop. And while. Okay. Yeah, you have a? Yeah, so multiple roots, we'll get there. For now and perhaps the next 1 or 2 lectures, we'll just consider there is only one root. We'll do one dedicated lecture on multiple roots. Okay, so this is fairly simple enough, and actually Rajat has an animation which I can just show. You need to put in your password. Something that you probably already expect to see, but yeah. This is for the function f of x equals x minus x. And you start at the extremas and you see it's getting halved, and it quickly converges. All right. Let me play one more time, just in case. Half, 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 half. So Now let us discuss about convergence. Does it always converge? And when it does converge, how fast does it converge? So I need to define some things here. If alpha is a root, by that I mean f of alpha is equal to 0. Okay? Then at the nth iteration, let's say I have this Cn. So alpha minus Cn or you can use Xn if you like, is your error. Okay? The difference from the actual root, which you don't know, and the iterate that you have converged to is your error. If the successive errors follow this relation more or less, then P is known as the order of convergence and A is the rate. That's definition, okay? This is definition of order and rate of convergence. Huh? En, E, error. Is definition. There's nothing to explain. If the successive errors are related in this fashion, this is an absolute value. The n plus 1th error in absolute terms is some constant times the absolute value of the nth iteration raised to the power some p, then that p is your order of convergence and A is your rate of convergence. It's a definition. If p is 1, then what is the order of convergence? P is 1? 1. So linear convergence. Okay. If P is 1, what will guarantee convergence? Greater than 1? Greater than 1, the error will grow. How will you converge? A is less than 1. Then the error keeps diminishing if P is 1. Successive error will keep diminishing. That will guarantee convergence. If it is greater than 1, it will amplify. Okay, so keep that thought in mind. And let us see whether the bisection method always converges or not in this particular case. You can also think of the Xn as Cn for the bisection method. Because we started at the two ends, A and B, we will probably get a sequence of subintervals, we'll call them A sub n and B sub n, which have the following relation. So A and B on the extremas, that's our initial interval, correct? Then we started finding C, that C was either assigned to A or B, depending on which side. Again, you have a B2 and a A2. which may or may not be the same as the previous A, depending on to what C gets assigned to, and so forth. So let's say we have this sequence, okay, and in fact at some point here I have an A sub n and a B sub n. Does everyone agree the iterates for the boundaries A sub n and B sub n must satisfy this relation? Because A moves from A to the right, the problem goes like this, like this, like this. So the A iterates are going up. It's equal to, because if at some point the C gets assigned to the B, which is B2, let's say, then A2 is the same as A1. That's where the equality comes in. Otherwise, the inequality comes in. So the sequence of A sub n is monotonically increasing, while the sequence of B sub n is monotonically decreasing in a continuous fashion. It's not like A increases and then a few A decrease and then the A's increase again. That's not monotonic, right? Monotonic means increase, 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 and only increase. This is from calculus 1 term. All right. So if I take, you see the interval A, B minus A is getting smaller and smaller and smaller. I might want to check what happens to the length of the interval after many iterates. What do you think will happen to this number? Well, what happens, how can I write B sub n minus A sub n? Well, let's try with n equals 1. What would that be? B1 minus A1, what do you think that will be? Huh? The entire range is B naught minus A naught. Half of the range, because C is midway through. Either it gets assigned to A or it gets assigned to B. I have halved the subinterval. So B1 minus A1 would be B minus A divided by 2. B2 minus A2, half of this. So B minus A over 2 squared. Correct? And half again and half again. So Bn minus An would be B minus A over 2 to the n. If I take this limit, this goes to 0, which means limit A sub n is equal to limit B sub n tends to infinity alpha. So these sequence converge to alpha for sure. That much we know. But is that alpha to which these iterates successively converge, is that the root? That's the question. We don't know that yet. We only know that the iterates converge. It may not converge to the root. There is no guarantee. So let's see whether this convergence point happens to be, I am interested in looking at the length of the intervals, the boundaries, the difference between the boundaries, right? So my initial difference is B minus A. After the first iterate, after I've gone past one swipe of that while loop, I have my B1 and A1. Either B1 is A plus B by 2 or A1 is A plus B by 2, correct? Either way, what is the distance of the subinterval now? B minus A by 2. Now B minus A by 2 is my length of the interval what happens in the next iteration? It gets halved again. So b minus a over 2 square, so and so forth. After n steps, I have b minus a over 2 to the n. When n is large, this limit goes to 0, which means the limit of this monotonically increasing sequence and the limit of the monotonically decreasing sequence, the a sub n's and b sub n's, converge to alpha. Good. I know these sequences converge, but do they converge to the root? I still don't know. So what would I do? Any ideas? What would I do? Well, I know A was on one side of the root and B was on the other side of the root. Correct? And my next sub-boundary that happens to be true again, A1 is on one side of the root, on the other side of the root. Same thing for the second iterate. Same thing for the third iterate. So, f a sub n times f b sub n is always less than equal to 0. Unless one of them happened to be the root, it's always less than 0. Because that's how I'm setting the boundaries. I'm keeping the root in the middle. That's how C is being chosen. What happens if I take the limit? N tends to infinity. Well, this is f of limit, because f is a continuous function. I can take the limit inside. If you recall from your calculus 1, if you do, the limit can go inside times limit n tends to infinity b sub n less than equal to 0. What are these limits? We just found them. Alpha. So this is f of alpha. This is also f of alpha. So I have f of alpha square less than equal to 0. When can this be true? Only when f of alpha is 0. So this limiting point actually happens to be my root. So the method converges, and not only does it converges to the root that I am looking for. This completes the justification that this iterative approach will converge and converge to the root. Questions? This is my limit n tends to infinity alpha. So both these are f of alpha. That's f of alpha whole square. When can a square of a number be less than equal to 0? When that number is equal to 0, which is what we're looking for, f of alpha equals 0. That alpha, which is the convergence point, is the root. Okay, good. We know that these iterates converge, and they converge to the root. Let's find out how fast do they converge to the root. And then we will be done for today's lecture. How much time do we have? We have ample time. 20 minutes, ample time. Ample time. Okay. Nth leftmost boundary and nth rightmost boundary. Okay, that's right here. say after n iterations, f of an times f of bn is less than 0. Check that. Cn is an plus bn over 2. Right? So either we have an comma cn as the boundary, sub-boundary now, or cn comma bn, depending upon the sign of fan times f of cn. That's where we are. Now let us say we want to find an estimate of the error, so we will be checking this entry, right? Because that's my estimate for error. Well, let's draw. I have A here, B here, alpha is here. This alpha I don't know yet. Alpha is the root. And let's say Cn is somewhere here. Could be on either side. The argument could still hold. Alpha minus Cn in magnitude must be surely less than B minus A. Let's call this Bn and An. Bn minus An divided by 2. Do we agree with that? Because Cn is at the midpoint, right? So this is the midpoint. This is the distance from the midpoint. And this distance will be less than half of Bn minus An. And I can continue that argument further. So this is less than Bn minus An over 2. This is evident from the picture. I can continue that argument and say this is also true. Why can I say that? Well, let's see. Let's see. I can write with blue. And let me write Bn minus An. Okay? And let's say this An happens to be my Cn. Bn minus Cn. So what is that Cn? That Cn happened to be An minus 1 plus Bn minus 1 divided by 2. Okay? When that was the case, this Bn was actually my Bn minus 1. So this is what I have. And then I have this. This is for Bn minus An, but there is a 2 already sticking out here, so this becomes 2 squared. I can continue going further all the way down to B minus A raised to the power 2n plus 1. This is my E sub n. Is it n plus 1 or just n? N plus 1. Yeah. Could be either. Minus 1. So that's Cn minus 1. This is Cn minus 1, which is An minus 1 plus Bn minus 1. So this is my En, right? So hold on to that thought. I know that this goes to 0. You can take the limit n tends to infinity, this goes to 0. What would I write for E sub n plus 1? what would I write? How will I bound E sub n plus 1? Just by inspection, by looking at the relation for B sub n, E sub n, divided by 2. Yeah. Equate so what happens here? C is the one which gets assigned to A. Correct? So my new A is actually my previous C. That's what I'm doing, halving, right? And that midpoint is my new boundary. So that becomes my new A sub n. That's what I've done. Yeah, the index is just how you write the loop, how you set the index in the loop. But essentially, my midpoint, which is my C, gets either assigned to B or A. You can do this for B as well. I've just shown you the case for A. And try the argument by setting the C to B sub n and keeping the A as such. You will get the same result. All right. Yeah. So this is just half of the earlier one, just by inspection. Compare the index n, and you will establish this relation. Okay? So what does it say? It says that if now I'm going to do some slight hand waviness, but I'll use pictures, so that should justify the argument. I have my B sub n minus A sub n, right? It is going to 0. B sub n minus A sub n is going to 0. So it is something like this. This is my B sub n minus A sub n. And my En is always bounded by this. So my En is somewhere here. This is my magnitude En. All right. Half of Bn minus An will be less than this curve Bn minus An. In fact, it will be exactly half. So midway through, midway through, midway through. So this is my Bn minus An by 2. And E sub n is upper bounded by this new curve. That's the picture I have from those relations. En plus 1 is always half of E sub n mod of E sub n, especially when n tends to infinity. As you can see, these things will get squished. Very large. I can almost say E sub n plus 1 is like my half of E sub n. This picture tells you that. This P is equal to 1 here. So I have linear convergence for the bisection method. So it's slow, linear is slow. And my rate of convergence half, so I'm guaranteed to converge as we decided earlier. Okay? So this bisection method, it always converges, and it converges linearly with the rate of convergence equal to half. In the next class, and I've also shown you one example through the animation. In the next class, we will look at another type of iteration, iterative approach, the Newton-Raphson and the secant approach. I don't know whether we'll do both or not, but maybe how I feel like. And then, of course, we have the fixed point iteration. So this will complete your 3 or 4 different numerical techniques. Of course, you will now implement this in your lab. They'll implement this in the lab in next week's lab. So you'll write a small Python code. How long? I mean, it's not very long, right? 3-4 lines. And answer some questions around that so that you get a handle over the bisection method. All right, so we'll close here today. Before we go, any questions? I have sent you guys the syllabus. Everyone has the syllabus. The only thing that is not mentioned is that it will be best of the two quizzes, but I've mentioned that to you in class. So it's not quiz 1 and quiz 2, 5 points, but each of them are 10 points worth. I will take the greatest of the two or the best of the two. Thank you. The other recordings, he just figured out where the folder is. I'll share with you. हाँ? वो उनकी मर्जी है, चेक करें ना करें. The attendance is always getting updated every week, so make sure that you keep a track of that. Thank you.